Okay, so welcome back. I I saw that I should say, well, I didn't exactly see this, but I was I had told your TAs uh, to actually I still haven't nicely listed all of the sections Zoom links, so they're still scattered in announcements, but I can do that on the syllabus page. I've only listed like half of them right now, but hopefully that wasn't too confusing for you. So that's how the discussions are going to be conducted. As I said, there may be instances where some small amount of work is collected in a discussion, but I will let you know when that's going to happen. Um, last time we had discussed, I had listed out all these things that are required for a matrix to be in row echelon form or reduced row echelon form. So last time, see, I don't know what I was thinking about. So two definitely implies three. I know there's questions about that, whether there was something that whether there's a matrix that satisfied three but not two. No, two definitely implies three. It's just that three is kind of added for emphasis here. Uh, because this is important, but really one and two are all you need here. So one and two you definitely need. You get three automatically, and four and five you definitely need for this thing to be in reduced row echelon form. So then some pictures of what this thing looks like, right, are here, as we saw last time. So these are examples of two matrices in row echelon form, not necessarily reduced row echelon form. Here's two matrices in reduced row echelon form. The purpose of reduced row echelon form is that in all these row operation computations that we're going to be doing, uh, basically what it means is that it guarantees that this process terminates in some unique thing. So if I ask you all to, for instance, if I give you a matrix and I say perform row operations on this matrix until it is in row echelon form, okay. Then if I were to give you that quiz and hand it off to a TA to be graded, right? I'm not going to dirty my hands grading it. I'm going to hand it off to be graded. So I'm going to hand it off to be graded. When they go to grade that thing, what happens? Well, if I just specified row echelon form, then there's some different answers that you could have. And we're going to see examples of that, right? Like the point is that there is no unique row echelon form for a matrix. There are many different sequences of row operations that could get you to a row echelon form matrix that is different from a row echelon form matrix one of your classmates may have gotten, although both of you are correct in having reduced the the matrix to something that is row equivalent to what your classmate said it was, right? So you have two people. They have both row reduced matrices to row echelon form. The matrices on paper look different, right? There are entries that disagree, okay, but they both use proper row operations, right? So the point of reduced row echelon form is if I went back and told you in the quiz to instead put the matrix into reduced row echelon form, there's only one answer. So it'd be really, really easy to be graded in that case. Yes, exactly. There is only one reduced row echelon form. So what I was saying before is row echelon form. So there is row echelon form. There's many of those, but there's only one reduced row echelon form, which is why it's important. Okay. So that's the important bit, and that's this fact that I've started here. Each matrix is row equivalent to one and only one reduced row echelon matrix. Okay. All right, so a quick definition, and then I'm going to write something that is very important. I might even take a whole page to write it. So quick definition. So a pivot position. So a pivot position is a matrix, or in a matrix A, is a location in A that corresponds to a leading 1 in the reduced row echelon form of A. A pivot column is a column of A that contains a pivot position. There's another, I guess I should say there's another term that goes along with this, which is a pivot itself. A pivot is a number occupying a pivot position. Pivots as numbers are not as they're not as important as the pivot positions themselves. That's the most important thing. So then going back to our picture here, where are the pivots, or where are the pivot positions, I should say? They're these black squares. Okay, so these black squares are the pivot positions, and the columns containing them are pivot columns. Okay, so this matrix only has 2 pivot columns. This matrix has 1, 2, 3, 4, 5 pivot columns. Okay, and you can see that these are indeed pivots because right below are these matrices put into reduced row echelon form, and those black squares exactly match up with where the 1s are here. Okay. Now, what is the purpose of pivot positions, pivot columns, number of pivot columns? What is any of that? Why am I giving these special names? We're going to define some things for matrices that use these terms. That's the main thing. These are an example of certain invariants of matrix, meaning that it's an underlying property the matrix has that turns out to be really important. Okay. For characterizing behavior matrices. So do I have enough room to write what I want to write here? Maybe. Let's try here. So this is the fundamental thing that you should, this is kind of the most important thing that you should know about this course for now. So lots of stars here. So this is, for the first good chunk of this course, for most of the course actually, this is kind of the most important thing. But almost every question in this course that can be asked of you is solvable by putting some matrix into reduced row echelon form. Okay. It's not exaggerating. From today until basically the end of the course, almost everything I could ask you to do, there's only a couple of exceptions, almost every question I could ask you, almost everything I could ask you to do is solvable by putting a matrix into reduced row echelon form. Okay. So what does that mean? It means that you have to get good at this. All right. You have to put a matrix into reduced row echelon form so many times, hundreds of times in this course, so that you have to be proficient at this. Okay. This is something that you have to get used to doing. And in lecture, while immediately, in these next few examples, I'm going to go through every step in the process, eventually, like very soon, I am going to skip that entirely. I'm going to write a matrix, and then I'm going to say, all right, I'm going to put this matrix into reduced row echelon form. Boom, it's in reduced row echelon form, and that's it. Okay, that's all I'm going to say. Okay. So that's how it's going to go typically. So after, in another 1 or 2 weeks, I'm not going to go through that process anymore. I'm just going to assume that you all are proficient enough. So if you're not, it's a good time to practice because we're going to be doing this over and over and over again. Okay, over and over and over again. Okay. So then what is this process for putting something into reduced row echelon form? So maybe I should do an example, and then we'll list out the process. I'm not actually going to write out the entire process. I'll just show you all where it is in the textbook and go through the steps one at a time. So here's an example. Row reduce the matrix A to row echelon form. Okay. All right. So the matrix A in question is reading row wise. This is 0, -3, -6, 4, 9, -1, -2, -1, 3, 1, -2, -3, 0, 3, -1, and 1, 4, 5, -9, -7. Okay. So what do I do here? The idea is that I want to put a convenient thing, hopefully one, and in this case I'm going to be able to do it pretty easily, in this first upper left position. Okay, I want that to be a 1. Okay, now there are instances where in this process you're not going to make this a 1 immediately. I will talk about that in a second. But in this case, if I swap rows 1 and 4, right? So if I swap row 1 and row 4, then I've put a 1 in that spot. So all the other rows remain the same. So this is just 1, 4, 5, -9, -7. The other two rows are exactly identical. I'm just going to copy them. And then my last row was my previous first row. 0, -3, -6, 4, 9. Okay. Now, having this 1 here makes it easy to zero out the entries beneath it, right? And I can do that in one go. So to zero out these 2 entries beneath this 1, what do I need to do? Well, all I need to do is add row 1 to row 2 to zero out that -1. To zero out the -2, I need to add 2 times row 1 to row 3. So I need to add row 1 plus row 2, replacing row 2. And I need to add 2 times row 1 to row 3, replacing row 3, right? So remember, our convention is the thing that comes second is the row getting replaced here. Okay, so when I do that, what do I get here? So my rows 1 and rows 4 aren't changing, so I can go ahead and copy those. Okay. And then so row 1 plus row 2, that's not so bad. So 1 plus -1, that's 0. 4 plus -2 is 2. 5 plus -1 is 4. -9 plus +3 is -6. And -7 plus 1 is -6. Okay. And then this third row is, so 2 times 1 plus -2 is 0. 2 times 4 plus -3 is 5. 2 times 5 plus 0 is 10. 2 times -9 plus 3 is -15. And 2 times minus 7 plus minus 1 is minus 15. Oh, look how nice that turned out. Right? Okay. So, continuing on, what is the idea here? So, the idea is that what I have done really is I have swapped a pivot into this slot. So this is a pivot position, okay? And then I used that pivot position to clear out the entries below it so that everything becomes 0. The idea then is that I want to identify a pivot position that is now to the right of this 1. Okay, it's to the right of this 1. And so here is where that pivot position is. And I want to use this pivot position to clear out the entries underneath it. So for row echelon form, I only care about clearing out the entries underneath it. Okay, so what do I do? What do I do here? I want to use this 2 to clear out these entries 5 and minus 3 here. Well, as they're written, this is kind of annoying to do. Okay, at least just looking at this. So then what do I do? How do I actually take care of what I have going on here? What do I do here? So it turns out in this case I'm lucky, right? But and why am I lucky? I'm lucky because these two rows are actually multiples of each other. Okay, so I can do an addition that, might on paper look kind of bad, but I can zero the 5 in without doing any kind of, you might be tempted to look at this and and reduce divide all these by 5, right? Multiply the whole thing by 1/5. You can definitely do that. Okay, you might be tempted to look at this row and divide all that by 3, right? Or multiply by 1/3. Okay, which would leave you with a 4/3 here, which is kind of annoying. But let's not do that. Let's not do that quite yet. So let us add, say, or multiply, say, minus 5/2 times row 2 plus row 3. What do I get when I do that? Minus 5/2 times 2 is minus 5 plus 5, that's 0. Here, this would be minus 10 plus 10, that would be 0. Here, this would be, it would be plus 15 plus minus 15, that's 0. And here it would also be 15 plus minus 15, which would be 0. So this is actually going to zero out my third row entirely. And then I can multiply, it turns out everything is nice here if I multiply 3/2 times row 2 and add that to row 4. So this is going to work out perfectly fine. Doing this, so the first two rows are completely unchanged. This is 1, 4, 5, minus 9, minus 7, 0, 2, 4, minus 6, minus 6. This third row, as we saw, is actually all 0. What does the fourth row become? So 3/2 times 2 is 3, plus minus 3 is 0. Okay. 3/2 times 4 is 6, plus minus 6 that's also 0. Okay. 3/2 times minus 6 is minus 9 plus 4, so that's minus 5. And then 3/2 plus minus 6 is minus 9 plus 9 is 0. So a lot of zeros come from that. Now, I will caution you here that in this case, this worked out nicely. Okay. But when you're doing these row reductions, a lot of times you want to avoid using rational numbers like this if you can help it. Sometimes you can't. Sometimes you can't help it. Sometimes the arithmetic involved is going to be nastier. There's nothing you can do to fix that. But the reason why is that a lot of times for some just generic matrix, you're just going to end up getting a bunch of fractions. And even though the end result will ultimately be the same thing, that process is just going to be a lot nastier to go through because you have a bunch of fractions showing up. And so you have a big matrix, that has like 30 something entries. You have a bunch of fractions you have to keep track of, right? And not all of them are even going to be nice fractions. So it's going to be annoying. So for that reason, a lot of times when you're doing this, you would look at this step and you'd say, oh, well, I'm because all these are multiples of 5, I'm gonna multiply by 1/5 here so that those numbers are simpler, and you're gonna proceed like that. So again, there's different paths to get you there, but this is just one example. So in order to put this in row echelon form, I can't have any row of zeros above a non-zero row, so I need to do a row swap here. So row 3 and row 4 get swapped. And we are good to go as far as row echelon form is concerned. Okay, so what would I do if I wanted to put this into reduced row echelon form? What would I need to do? So what is stopping this from being reduced row echelon form? Well, there's a couple of things, okay? These pivot positions would all need to be 1. Okay, these leading entries all need to be 1, so those need to be 1. So squares need to be 1. This is one thing. Okay, one of them is, but these two aren't. Now, making those 1, that's not a big deal, right? That's not a big deal at all. It's not too bad. And then the second thing is that all entries above and below the squares need to be 0. Okay, which means that entry needs to be zeroed out, and these two entries need to be zeroed out. Okay, so I would need to do additional row operations to do that in order for this to be reduced row echelon form. Okay, so the question is, are we always going to be putting things in reduced row echelon form? Many times we will. A lot of times we won't because we don't need to, because a lot of the questions that we're going to be asking will allow us to already see the answer from, say, row echelon form. Now, what do you mean by that? Remember that all this stuff that we're trying to do ultimately was because we wanted to solve linear systems. So if I have some question about the solutions to a linear system, a lot of time those questions can be answered just by looking at the matrix. After a couple row operations, you've got the linear system. So now you're not thinking of the matrix anymore, you're thinking of the linear system associated to this. So you see this and you're like, oh, well, now I see that it has a solution, right? Or it has this property that I was looking for. Okay. All right. And so this is the idea. All right. So many times we'll be putting things in reduced row echelon form. Sometimes we won't. So then what is the actual algorithm? Okay. So let's see. Let's make sure that this is not too blurry, since I'm going to hold it up a little bit. Maybe I'll refocus it. I have to hit this little button. Okay. Row reduction algorithm. So here's my example. Here's my very long matrix here, this 3x6 matrix that's listed there. This is the algorithm that shows you why this thing always terminates. Okay, and basically how to do this. Not necessarily the most efficient way, but it's a way that guarantees you don't go backwards. So begin with the leftmost non-zero column. This is a pivot column. The pivot position is at the top. Okay. So in this case, we want to swap a non-zero entry into that slot. Okay. That's the idea. Okay. So step 2, I'm a little out of focus here. So step 2. Select a non-zero entry in the pivot column as a pivot. If necessary, interchange rows to move this entry into the pivot position. So here's pivot column, and interchange rows 1 and 3. So this is what we got. We've swapped our choice for pivot into this top left position. Okay. All right, so then step 3, use row replacement operations to create zeros in all positions below the pivot. That's exactly how we did in our process before. So now this 3 has zeros below it because I've used row replacement to replace row 2. Okay. Step 4, cover or ignore the row containing the pivot position and cover all rows, if any, above it. Apply steps 1 through 3 to the submatrix that remains. Repeat the process until there are no more zeros or rows to modify. So the idea is that basically you ignore the first column and this row and you do that same process for what is left. Okay, so everything in blue, you're not thinking about that right now. You're looking at this matrix that's left and you do the exact same process. Okay, so you move pivot. If you don't have a zero in the, or if you don't have a non-zero entry here, you swap one so that you do, if possible, and then you zero out everything below it. And then once you have gotten all these zeros, here, I was pointing to stuff that was off screen slightly. So once you've gotten to this point where you've zeroed out everything below it and you continue on, so this is a small matrix, but once you've gotten to this point, you have a bunch of zeros here. Now comes the step when you're zeroing out everything above. So you zero out everything below in the first bit. That's exactly what we did in our example. Let me bring that back. Right? But then to get to row echelon form, I needed to zero out these entries above. So I need to do these same sorts of row replacements, okay, to zero out these entries. Why did I wait until I have a bunch of these zeros here? Well, if I don't, then when I do the row replacements to zero out the entries above, I have non-zero entries here that get added and they change the stuff above. So I've essentially gone in a circle if I do it that way. Or I've done something very, very inefficient because now you're thinking of like a Rubik's Cube or something, or like some kind of puzzle that you're solving, in sequence. The point is that you're undoing some of the progress you've made in this way if you don't have these zeros here. So if you try to zero out these entries above the pivot positions and these aren't all zeros, you're going to change these positions. It's going to undo some of the work you've already done. So that's no good. Okay. And so beginning with the rightmost pivot and working upward and to the left, create zeros above each pivot. So in this case, that would be starting here. Right, at -5, you'd zero out these and then work your way backwards. Okay, so working upward and to the left, create zeros above each pivot. If a pivot is not 1, make it 1 by a scaling operation. Okay, so that's simple. That's just multiplying by 1 over whatever that thing is. Okay, so as it says here, so ultimately this results in the following. This is the reduced row echelon form of that matrix that was started with. So you see how the pivot positions are all 1s now. Everything is 0 above them. So steps 1 through 4 are called the forward phase, and step 5 is the backward phase. So the forward phase is the thing that we did to produce row echelon form. The backwards phase is the thing that gets the reduced row echelon form. So the backwards phase is all that's needed to go from row echelon to reduced row echelon. Okay, so we are going to be doing that algorithm a ton in this course. In fact, you're going to be doing it like constantly. Okay. So here's the point. So this is going to be applied to almost every, so this will be applied to almost everything we do. All right. But the first application we could talk about is in like solutions to linear systems. Okay, so how do I apply this to solutions to linear systems? The idea is the following. So suppose I have a system with augmented matrix. That is 1, I'm reading row-wise, 1, 0, minus 5, 1, 0, 1, 1, 4, 0, 0, 0, 0. Okay. All right. So suppose I have a system like this. So this has already been put into reducer row echelon form. So this is already RREF. So this is in reducer row echelon form. So I don't need to do anything. Once I've got it in this form, it might have started as any other matrix that's row equivalent to this that's not in reducer row echelon form. But here I have it in reducer row echelon form. Let's write the corresponding linear system. So this corresponds to the linear system, which is x sub 1 minus 5x sub 3 is equal to 1, and x sub 2 plus x sub 3 is equal to 4. And then this last line would be 0x sub 1 plus 0x sub 2 plus 0x sub 3 is equal to 0. So that's 0 is equal to 0. That actually gives me no new info, really, right? This gives me no new info. And so ultimately in this system, even though I have 3 unknowns, x sub 1, x sub 2, and x sub 3, I only have 2 equations here that are actually conveying any info. Okay. Now, the variables x sub 1 and x sub 2 are called basic. That's not something that we're going to use a lot. That's not something we're going to use a lot. The variable x sub 3 is called a free variable. Okay, and we are going to use that quite a bit. What do we mean when we say x sub 3 is a free variable? Okay, what this means is that the solution to this system can be solved in terms of x sub 3. Now maybe there's more than one free variable, so maybe it's not entirely in terms of x sub 3, but the point is that the solution in some way depends on a choice of value for x sub 3, and that choice is free. That choice being free means I am free to make that choice completely arbitrary. That x sub 3 value can be whatever. Okay? All right. So, this choice of x sub 3 can be seen if I actually solve this just by doing a simple, if I solve this for x sub 1 and x sub 2, so a solution to this system is of the form, I'm just going to look at these equations. I don't need to do anything fancy here. I just move 5x sub 3 to the other side, right? So the form of a solution is x sub 1 is 1 plus 5x sub 3, and x sub 2 is 4 minus x sub 3. And x sub 3 is free. You can write in is if you don't like having, nothing in there. So x sub 3 is free. This is the solution to this linear system. Okay, so what do I mean by this? What I mean by this is each choice of x sub 3 yields a different solution. So each choice of x sub 3 yields a solution to the system. And x sub 3 can be whatever you want it to be. So when x sub 3 is 0, what's my solution? It's 1, 4, 0. Maybe I should do that on another sheet really quickly. So I'm going to leave that here. Okay, so then on this other sheet, if x sub 3 is equal to 0, then x sub 1 is equal to 1 and x sub 2 is equal to 4. So a solution is x sub 1 equals 1, x sub 2 equals 4, x sub 3 equals 0. And if x sub 3 is equal to minus 1, then x sub 1 is 1 plus minus 1 times 5, so it's 1 minus 5, so that's minus 4. And x sub 2 is, so this would be 4 minus minus 1, so that would be 5. And so a solution would be minus 4, 5, minus 1. Okay. So let's think about this for a second. We already know that for a linear system, the possibilities for solutions are no solution, one solution, or infinitely many solutions. So the existence of a free variable is exactly what causes this to happen, right? So the existence of a free variable tells you you have a free choice here, and each choice yields a distinct solution. So there you go, right? This is the way that infinitely many solutions creep into this this situation. Okay, so really quickly, here's an example. So find the general solution to the linear system whose augmented matrix has been reduced to the following. Again, reading row-wise here. This is 1, 6, 2, minus 5, minus 2, minus 4, 0, 0, 2, minus 8, minus 1, 3, and 0, 0, 0, 0, 1, 7. Okay. So from here, I'm going to put it into reduced row echelon form. So how do I do that? Let's see. So nothing needs to be done here for the first two. Here's my pivot position I want to use and zero out everything above it eventually. So let's see, I'm actually good. This is in row echelon form. So then what do I do here? I'm in the good position to actually zero out these two entries. So I zero out these two entries by taking 1 times row 3 and adding it to row 2. So row 1 plus row 2, row 3 plus row 2, and row 2 gets replaced. And also I do 2 times row 3 plus row 1. Row 1 gets replaced. So row 1 and row 2 are being replaced. Row 3 is unchanged, so that's 0, 0, 0, 0, 1, 7. Okay, row 3 plus row 2, so this is 0, 0, 0 plus 2 is 2, 0 plus minus 8 is minus 8. Those are unchanged. That's what having these zeros here helps us with. 1 plus minus 1 is 0. 7 plus 3 is 10. Okay, and then 2 times row 3 plus row 1. For the first 4 entries, nothing is changed because 2 times 0 is 0. So this is 1, 6, 2, minus 5. And then here I have 2 times 1 plus minus 2, so that's 0. And now I have 2 times 7, which is 14, plus minus 4, which is 10. Okay. So now what do? I want to identify the next pivot that I'm going to switch to 1 so that I can zero out what's above it. So here I want to reduce this by, I want to scale this by 1/2. So 1/2 times row 2. I'm going to go ahead and copy that here so that I can do this next bit in the same matrix. So 0, 0, 1 minus 4, 0, 5. Okay, the third row is unchanging. And this first row, I want to add, now that I've changed this row 2, this can be tricky doing this at the same time, but now that I've changed this row 2 in this way, I want to do the next operation on this changed row 2. So I want to do minus 2 times row 2 plus row 1. Okay, so in the first two entries, nothing's changing because those are zeros. Now I have minus 2 times 1. Make sure you don't go back and do this, right? So I have minus 2 times 1. So minus 2 times 1 plus 2, so that's 0. Then I have minus 2 times minus 4, which is 8, plus minus 5, which is 3. And then I have minus 2 times 0 plus 0 is 0. And then I have minus 2 times 5, which is minus 10, plus 10 is 0. Now, what do you notice about what I just did? Right? Yeah, so, and someone said it doesn't have to come first, it just matters that the result's correct. And that's right. I'm not trying to imply this is the only way to do it. In fact, you might notice that I did something here that I didn't really have to do. I changed this row, and then I did this row replacement. But could I have actually done the same row replacement without changing this row first? Yeah, why didn't I just do minus row 2 plus row 1? That would have done the exact same swap here. The only thing doing this multiplication matters is that doing this in one matrix means I just don't have to copy it down. This is now the reduced row echelon form, and I don't have to zero this out anymore. But really, I didn't really save much time here. Okay, and this is not a unique process. You could have done this in another way, but this answer you get is unique. Okay. So it doesn't matter what process you used here, this thing that you get is always going to be the same for the matrix you start with. Okay, so there it is in reduced row echelon form. Now that I have it in reduced row echelon form, I have a nice way of describing how to write out a solution to this. So I'm finding the general solution to a linear system that has this. So if I write the corresponding linear system to this thing, what does it look like? The corresponding linear system looks like x sub 1 plus 6 x sub 2 plus 3 x sub 4 is equal to 0. Okay, and then the next line is x sub 3 minus 4 x sub 4 is equal to 5. And then the last one is x sub 5 is equal to 7. So then this is my linear system. What does a general solution look like? So then the general solution is x sub 1 can be written in terms of x sub 2 and x sub 4. So minus 6 x sub 2 minus 3 x sub 4. X sub 2, well, x sub 2 isn't here. I've already written x sub 2 up here. I can write x sub 1 in terms of x sub 2 and x sub 4. X sub 2 is free. And x sub 3 is 5 plus 4x sub 4. And x sub 4 is free. And x sub 5 is equal to 7. Now, a couple questions. What do you notice about which variables are my free variables? Okay. So, my free variables are, let's put the variables by the columns that they're associated to, right, in the augmented matrix. So here I have x sub 1, x sub 2, x sub 3, x sub 4, and x sub 5. These are the columns that are, don't think that I'm writing them for this matrix. I'm writing them above this matrix that I've boxed in here. Okay, so what do you notice about my free variables? So my free variables come from the columns that don't have pivots, right? They come from the columns that don't have pivot positions. All right. So that is exactly the characterization of free variables. The basic variables, like I said, we're not going to use that term that much, but the basic variables come from the columns that have pivot positions, that are pivot columns. But the free variables come from the columns that don't have pivot positions. So note, free variables come from the columns without pivot positions. So the non-pivot columns. We are going to discuss this at length a bit later, but this is the idea here. Okay. All right. So I'll talk a bit later also about the parametric form of this, but after we talk about vector equations. So then one big thing, right? So as I wanted to say before, so big question is existence and uniqueness. For linear systems. Okay, that's not really phrased as a question, but the answer to when linear systems have solutions, that is when solutions exist, and when those solutions are unique, is answered by the following theorem. So the answer is the following. A linear system is consistent if and only if the rightmost column is not a pivot column. Rightmost column of what? I didn't even say. The rightmost column of the augmented matrix. The augmented matrix associated to the system. Is not a pivot column. Okay. i.e., if and only if an echelon form or row echelon form of the augmented matrix does not have a row of the form 0, 0, 0, 0, B, where B is not 0. Okay. Exactly. So as someone said, you can see that in the row echelon form without necessarily having to go to reduced row echelon form. Yeah. Because if you get this, there's no need to reduce this B to be a 1. It doesn't matter that B is, whether B is 1 or not. All that matters is that B is not 0. Okay. All right. Okay. Now that answers the question of when it is consistent. Consistent meaning has at least one solution. So that answers the question of existence, but it doesn't answer the question of uniqueness. So then when do I know that a solution is unique? So if, of course, for it to be unique, the solution has to exist in the first place, so it's got to be consistent. So it's already got to be in this case. All right, so if a linear system is consistent, then the solution set contains either one, a unique solution, or two, infinitely many solutions. Okay, well, we already knew that. So then what classifies these cases? You get a unique solution when there is no free variable. And you get infinitely many solutions when there are free variables. I.e. at least one free variable. We'll get you there. Okay. So at least one. Okay. All right. So it is about that time since we started at 102 and it's 153 now, so it has been one more minute than 50 minutes. So I think that's about time. This is a good place to stop anyway. So Friday I will continue on with this. Basically, we should finish like another half of chapter 1 on Friday, so that we'll basically be recasting all this stuff using different terminology. But this is the basic stuff. So even though we're only in 1.2, this is the stuff that we're going to be using this stuff literally for the entire rest of the course. So get used to it. This is how it's going to be. All right. So looking here. Nope, I think that's pretty much all the questions. So anyway, yeah, so I will see you all on Friday, and I will any changes to stuff like lecture schedule and stuff I'll post on announcements. I'll actually post a lecture schedule sometime later. I meant to do it last week, but it's not a big deal. So I'll post a lecture schedule and upload it to files here sometime before Friday. But anyway, I will see you all on Friday.